In Chapter 3, loci of complex numbers, the word loci is the plural form of the word locus, which refers to a set of points that satisfies a condition. For example, if you are interested in locus of points same distance from 2 points A and B. So if you have 2 points A and the second point B, in two-dimensional plane, in 2D, okay, in 2D, the set of points which are same distance from A and B they are points along the perpendicular bisector of A and B. All points along this perpendicular bisector, they are all same distance from A and same distance from B. Like say a point on this line, it is same distance from A and same distance from B. So for this example, the locus of points which are same distance from A and B will be the perpendicular bisector of the 2 points A and B. As another example, if you want the locus of points 5 units from a point A, locus of points 5 units from a point A will be points which are like this. 5 units away, there will be points on the circle whose center is A and the radius is 5 units. So let me draw it more carefully. I meant to say all points which are 5 units from A, all these points form a circle, center at A and radius 5 units. Now, so locus represents set of points that satisfy a certain condition. In the earlier example, the condition was the points are same distance from A and B. In this other example, we are talking about a condition that is 5 units from A. In this chapter 3, we are referring to such kind of questions where we have a set of points that satisfies a certain condition. But in our chapter, the condition in this chapter, right, will always be in the form of what is called a complex number equation, or you'll be in the form of complex number inequality. So in this chapter, right, we are studying the same thing, a set of points that satisfy a condition. And our condition comes in these two forms, either in the form of an complex number equation or an inequality. Let us plunge right away into example 1. In example 1, part 1, we are given this equation and we want all points Z that satisfy the condition. What condition are we talking about? The condition is actually this complex number equation. We want all those Z that will satisfy this equation. If you look at this, right, if you look at this equation, very quickly you can actually guess, say the complex number 5i will satisfy this equation, right? So the complex number 5i will be such a point. Another possibility is the complex number minus I. When you put minus I into here, you will find that the complex number I will also satisfy the equation. So at the very least, by just glancing, you actually have two values of Z. But you know that there are many possibilities. And to actually identify all the Z values that will satisfy this equation, one way is to try to understand what this equation means geometrically. Geometrically, you want to realize that this expression on the left, Z minus 2i, this expression on the left has a geometrical interpretation. this expression on left, if you look at a diagram, if this is my complex number 2i, this is the real axis, and this is the imaginary axis. For any complex number in the Argand diagram, say like this, right? This is the complex number 2i, and say for any complex number z in the Argand diagram, where is the complex number z minus 2i? Z minus 2i is actually this complex number. This complex number is actually z minus 2i. You know that in complex number, you can have a choice of drawing the z like a vector, and then the 2i also like a vector. So I can actually represent a complex number, say 2i like this, like a green dotted line, and the complex number z, any ordinary complex number z, as also a directed line in green color like this. So in the Argand diagram, the complex number z minus 2i actually is this red color complex number. And you realize that it is very much like a vector. It's true. In some textbook, complex number on Argand diagram are represented very much like vectors. But you don't have to. We can just represent the complex number 2i as just a dot if you choose to, and then the complex number z, a generic complex number z, as just a dot, say here. But what's important is you want to know that if this is 2i and this is the complex number z, z minus 2i or z minus 2i is simply this red complex number. And now if you put a modulus here, the modulus of this complex number, if you look at this carefully, the modulus of this complex number, if you look at this carefully, it actually represents this distance. The modulus of this complex number z minus 2i actually represents this distance. So if you look carefully, geometrically, the modulus of z minus 2i actually represents the distance from 2i to z. Let me tell you why is it so. Can you see? Z minus 2i is like this, right? The modulus means this value, this distance. So put together, this expression represents the distance from the complex number 2i to z. So what happened here is the left hand side represents the distance from 2i to z, as explained here. Now taken together, this entire equation would therefore mean you want those z values where the distance from 2i to z is always 3. Alright, taken together, this entire equation means you want the distance from 2i to z to be always 3. So now if you have understood this geometrical meaning, you are ready to draw a diagram for it. This is my complex number 2i. And as explained earlier, taken together, this equation means you want all those complex numbers whose distance from 2i to the z is 3. So let's locate all those complex numbers on this Argand diagram, which are so-called, in this case, right, 3 units away from the complex number 2i. So one possible complex number would be a complex number here, 5i, right? And another complex number here, which is minus i. What other points will satisfy this condition that is 3 units away from 2i? It can also be a complex number here, where this is 3. It can also be a complex number here, which is minus 3 plus 2i. So I have quickly marked down 4 points which are so-called, which are 3 units away from the complex number 2i. This is minus 3, okay? How about other points that will satisfy the same condition? And you realize that as you go on, you find that actually there are many points that satisfy this condition. Where are these points that will satisfy this condition? There'll be all points on this circle. So you find that all points on this red circle, right? They are all 3 units away from the complex number 2i. So all points on this circle actually satisfy the required condition. Hence, judging from this diagram, we can say that the locus of point Z that satisfy this equation will be a circle, center at 2i. In this case, it's 0 plus 2i. 0 plus 2i, and the radius is equals to 3. Okay, so this is example 1, part 1. It ends up as a circle, center at 2i, and radius 3. So if you have understood this, then you can actually try to generalize an equation that will always represent a circle. Judging from here, you can then see that if I have an equation that's like this, if I have an equation that looks like this, okay, sorry, I can use Z0, okay? If I have an equation that looks like this, such an equation in general will always represent a circle, center at Z0, and having a radius equals to R. And that is example 1, part 1. In example 1, part 2, we are given yet another condition, or so-called the complex number equation, which serves as the condition. We want all those z values that will satisfy this condition or this equation. Now look at this equation and compare to what we have established just now. You can see there's some similarity, and you can therefore guess that this ought to be a circle. And to make corresponding conclusion, it is important for you to rewrite this equation to match the generic form of a circle. So for this question, what you ought to do is, you want to rewrite this thing as like this. After rewriting and then you compare with the generic form, you can see that this equation actually represents a circle whose center is at your so-called Z0, right? And the radius is 5. So with this correct interpretation, now we are ready to draw the diagram. The diagram will look like this. We draw it here. -3 and 4. This is the real axis, and this imaginary. This is 0, the center, the so-called the origin. So the center of the circle is here. -3 plus 4i is here. Now you want to draw a circle whose center is at -3, 4, and the radius is 5. So what you should do is, you should actually take an instrument set and draw this thing to scale. You will be able to draw a circle that will look like this. Okay, drawing freehand is not easy. Right, so you get a circle that's like this. What is important in this question is, when you draw your circle, you must try to make sure that you get some important feature correct. Number one, this is exactly 5 units. So you must make sure that the circle actually passes through this point. It's very important. Okay? And maybe I should actually improve on this drawing a bit. I should draw my y-axis longer. The imaginary axis longer. Right. Secondly, in drawing this diagram, right, in this diagram, you must clearly illustrate that this is a center. You must mark down somewhere on the diagram that the radius that you are drawing is 5. You have to mark this down on the diagram, otherwise you may lose marks for details. And sometimes you can even add more details. By symmetry, you can guess that this point is actually -6. Right? And likewise, by symmetry, you can guess that this point has to be 8. So if it's not too hard, to add in this additional information, you should actually put it down. Right? So when you draw your locus on the Argand diagram, to get a good diagram, I would strongly urge you to buy a instrument set and do your construction quite to scale. Let me improve this a little bit because I think that the drawing is a bit overlapping. Let me rewrite this thing as z minus -3 plus 4i here equals to 5. And let me join back the circle nicely. So what you have here is a circle, center at -3 plus 4i, and the radius is 5. So please remember that in this diagram, you go very careful to decide whether or not you pass through the origin. You have to indicate the radius very carefully. You have to put enough markings, enough details in your diagram. And you want to actually mark down the red circle as Z. All your Z lies on the circumference of this red circle. And that is your example 1 part 2. For number 1 part 3, for this given equation, you compare this equation with this equation, you'll find that this one seems a far cry from the generic form of a circle. For such a question, right, when it is not in the form of the general equation of a circle, you have to do some tidying up. How do we tidy up this expression here? On the left hand side, right, on the left hand side, I'm going to rewrite them as z plus iz plus 1 minus I. Okay, what have I done here is I have simply just expanded. I've just expanded this expression, this times this and this times this, and I put the z and the iz together. Then next is I will have 1 plus I okay. I want to be able to reach something like this. I want to be able to reach an equation where I just have a single z. And that prompts me to do this. That prompts me to actually do a factorization. So what I have done here is I have performed a factorization of 1 plus I. So when I factorize 1 plus I, this one will have 1 minus I over 1 plus I, because when you take this times this, you get back your 1 minus I. Then from here, if you have the modulus, of a product, I can change this to become modulus of the first complex number and then modulus of the second complex number. If you do your so-called division, if you do your division carefully, you will be left with this. You're left with this. Okay, all in, you'll be left with this. Right? You do your rationalization, all in, you'll be left with this. Okay, let me check my arithmetic. Right. Then you want to note that this modulus of this complex number is just square root 2, and then I bring it over to the right hand side. I will finally arrive at z minus I equals to 1 over square root 2. And now if you compare this final equation with this generic one, you realize that this equation actually represents a circle whose center is at I and the radius is 1 over square root 2. And now you are ready to draw this circle. Please mark down this as a real axis, the imaginary axis, the 0. The complex number I is here. Mark down as 1. Okay, mark as 1. And then the radius is 1 over square root 2. The center is here. The radius is 1 over square root 2. It's not too big a number. So your circle should look something like this. You must indicate in your diagram that this radius, right? You must indicate in the diagram this radius is 1 over square root 2. And then if your locus of point is on this red circle, you want to put this down as your z. So all the z that satisfy this equation are points on this circle. And then in words, you will say that it is a circle, center at I, and the radius is equals to 1 over square root 2. Right? The diagram, and if you have to describe the locus of point, is a circle, center at I, and the radius is 1 over square root 2. Right? And that is actually example 1, part 3. In example 2.1, or rather in example 2, right, we are going to look into another group of loci. In this case, in example 2, part 1, right, you are given this equation. For this equation, if you were to rewrite this equation, it becomes z minus 1 minus 2I. And then this can be rewritten as z minus. If you could recall, in the earlier discussion, I told you, if you have like this, if you have a statement that's like this, modulus of z minus 2I, if you could recall, this represents the distance from 2I to z. Right, distance from 2I to z. So in general, if you have z minus z1, modulus of z minus z1, it means the distance from to z, right? So with this in mind, with this understanding of a statement like this, we are now going to look into example 2 part 1. On the left hand side, after rewriting, this one means the distance from this complex number to z. The right hand side means the distance from this complex number to z. So put together, this equation means you want all those z values or the point z such that the distance from this to z and the distance from this to z are the same. In another word, you want those values of z which are same distance from 1 minus 2i and minus 4i. So you want those z, right? You want those z which are same distance from 1 minus 2i and minus 4i. So what kind of complex number will satisfy this needed condition? Now if you draw your Argand diagram and you want to explore from Argand diagram what kind of z values will satisfy this condition. So you draw an Argand diagram like this. Now always bear in mind to write this as real z, this imaginary. Now once again, I want to stress to you that it is very important for you to have an instrument set and to draw your diagram as accurately as possible. So the first point is 1 minus 2i. 1 minus 2i. So this is the first point, 1 minus 2i. And then the second point is minus 4i. Minus 4i is somewhere here. So what happened is you are looking for points z which are same distance from these 2 points. To have points same distance from those 2 points, it will have to be points which lies on the perpendicular bisector of these 2 points, right? All points along this perpendicular bisector, all points along here, right? They will all be same distance from this point, which is 1 minus 2i, and this other point, which is minus 4i. Now, in constructing a diagram, it is important for you to indicate that this is 90 degrees, and you should also do a marking to show that these 2 edges are the same length, so that together it represents the perpendicular bisector of these 2 points. So for this question, example 2 part 1, this is actually the diagram for this locus. And how would you describe this locus? You will say that it is actually a perpendicular bisector of 1 minus 2i and minus 4i. Right? In general, what kind of equation would result in like this case, perpendicular bisector? In general, what kind of a complex number condition or equation will result in a perpendicular bisector? Based on this example, you will write that the equation of this form, like this. Or equation of this form. If you have this on the left equals to this on the right, then geometrically this is interpreted as the distance from z1 to z is the same as the distance from z2 to z. Such an equation will always end up as a perpendicular bisector of the 2 points z1 and z2. That is actually example 2 part 1. As you can see, right, my line, now I look through the camera viewer, I find this line is not very nice. So in tests and exam, right, it's very important for you to use a proper ruler to draw it. I'm going to improve on it because it's important for you to get good diagrams. I hope now is an improved version of the earlier one. Right, okay, so of course I can't be that great, you know. So with freehand, but on your own paper and on your own paper using proper instrument, you must actually draw a proper perpendicular bisector like this. You must really indicate that these two are the same length. Someone will ask me, do we need to indicate this point? If it is not too hard, you can try to do it, no? But if it's too hard like this case, maybe you should just leave it, no? You should not try to actually attempt to even put down this value, no? You should just leave it, right? And now next again, in example 2 part 2, you are presented with another equation. If you compare this equation with the generic equation for a perpendicular bisector, you find that they are not exactly alike right away. So when that happens, you will always need to do some tidying up. So for this question, to tidy up, you want to do this. Okay, what have I done? I have simply factorized the minus 2i on the left. And on the right, I'm going to do something similar. Okay, so what I've done here is I've simply I've simply just done some factorization. Alright, after factorizing, I want you to know that this number on the left can cancel out with this number on the right. Why is that so low? Because the modulus of the complex number minus 2i is exactly 2. And this is also 2. So therefore, I can cancel away these two. Now I can rewrite a little bit more. I can rewrite this thing as what I have done here is I have simply multiplied by I to the denominator and by I to the numerator. If you multiply I to the denominator, you get minus 1 because I squared, right, is minus 1, which goes with this minus with a plus. And then on the other side, it is just the same, not much change. Not much has changed. I'm just rewriting. And then now to make this one look like this, I'm going to do a final rewrite. I'll rewrite this thing as z minus equals to so now if you look at this equation as compared to this, they now look alike. So based on your understanding of this generic one, this is actually a perpendicular bisector of the 2 points, which are minus I over 2 and minus 2 plus 5 over 2i. So now you're ready to draw a diagram. Okay, this again is the real axis, this is the imaginary axis. So mark down the complex number minus I over 2, which is here. Bear in mind though, you mark down as minus half, not minus I over 2 though. We don't put I along this axis, just minus half. Then minus 2, 5 over 2 I will be roughly, okay? Minus 2 and 5 over 2 will roughly be here. Right? So it's actually the perpendicular bisector of these 2 points. So I draw these two first, and now I use the instrument set to construct my perpendicular bisector. And once again, it is very important for you to remember to indicate on the diagram that these two are of the same length. You realize that I put this down perpendicular. And once again, if you ask me, do you need to write down what these 2 points are? My answer to it is, if you feel confident and you think you can do it quite easily, you can do it. Otherwise, just leave it. No, those things that are not so easily obtainable, you might just want to leave it. But you want to actually put this down as your origin 0. Okay. Always remember to state this as real and imaginary, and then to write your complex number z on the line. And there you are, example 2.2. In example 3, we are going to look into yet another group of loci. In this case, right? In this case, you are given an equation that deals with argument. Argument refers to the angle. And to understand this equation, what you need to do is, first and foremost, you want to rewrite this as argument of z minus 3 minus I. And then we want to recall our understanding of this expression. What is this complex number z minus 3 minus I? So what you should do is, on the Argand diagram, you want to first and foremost draw the mark down 3 minus I. This is the complex number 3 minus I. Right? If you have a complex number z like this, if this is my complex number z, alright? So you have, say, 3 minus I drawn as like a directed arrow, 3 minus I, and this is a complex number z, a generic complex number z. Alright? Where is this complex number z minus 3 minus I? Remember previously I told you that for a complex number, they behave somewhat like vectors. So the complex number z minus 3 minus I would be this complex number. This red vector here, this vector looking thing, this red vector looking thing, this is actually the complex number z minus 3 minus I. So what this question wants is, you want such a complex number to have an argument of pi over 3, which means you want this complex number z minus 3 minus I to have an argument of pi over 3. So what it means is, you want this angle to be equals to pi over 3. Alright. So for this equation, if my complex number 3 minus I is here, right? This is 3 minus I, and my complex number z is here. This is complex number z minus 3 minus I. So what the question wants is, you want those complex number where this red complex number has an argument of pi over 3. Let me polish up the diagram a little bit so you can see it better. Okay. This is, you want this to be pi over 3. So in this diagram, if this angle is truly pi over 3, then this point z is one such complex number that the equation desires. In this diagram, can you tell me what other points in this diagram will satisfy the same condition? I have one such point z. If this is truly pi over 3, then this point z satisfies this equation, right? Are there other points you can see in this diagram that will actually satisfy the same equation. How about say a point here? If I call this another point, another z, okay? If this is another z, then once again, if this is another point z, right? Once again, you can draw a line, dotted line here, this z, and this is my 3 minus I. And then this one through to this fella, right? This one from here all the way to this fella will be my new z minus 3 minus I. So such a point that lies along this, such a point, if it lies along this. So if I take another point, which lies along this line here, another point z here, this is z, this is 3 minus I, so this complex number is same, z minus bracketed 3 minus I. And as long as along this dotted line, you find that another point along this line, right, will also satisfy the same equation. And then very soon you realize that if I have another point here, it will also satisfy the same equation. Another point here. In fact, you find that all points along here, they will all satisfy this equation. So what are you going to have? You're going to have, say, in this case, right, the locus of points that you need will be points that is on this line. And as long as this angle is pi over 3, all points along this line, which is actually this line again, all points along this line, they actually satisfy this condition, the argument of z minus 3 minus I equals power 3. So let's bring more substance. This is the real axis, this is the imaginary axis, this is 0. Right, so therefore in this case, this equation defines points along such a line. For the same question, do you think that points along this side, if this point z, right, instead of here, if I draw it over there, will points along the side satisfy the same equation? Let's check again. If this is z, then this would be my z minus 3 minus I, right? So if you take a point over the side, you find that the argument of such a complex number is actually here, right? If you take a point on this other side, do you think that points on this other side, could they also satisfy this same equation? You find that if you draw points on this other side, the argument of such a complex number, is it pi over 3? It is not. In fact, looking at the diagram, the argument of this could be minus 2 pi over 3 because it's going the clockwise direction. So this angle is minus 2 pi over 3. So you realize that while points on this side satisfy this equation, you find that points on this other side right here, right, they don't. So therefore the locus of point that satisfy this equation will be just only this part of the line and nothing below it. To push you a bit further, do you think that a point here will satisfy this equation? Which means if your z is exactly the same point, 3 minus I, If z is exactly the same point as this, which means if z is 3 minus I, would this equation be satisfied? If your z is exactly this point, right? Let's see again. If your z is exactly this point, then your equation becomes what? No? Your left hand side becomes 3 minus I minus 3 minus I. And what do you have? A complex number 3 minus I minus 3 minus I gives you the complex number 0 plus 0I. What is the argument of 0 plus 0I? 0 plus 0I is just a point. There is no defined argument for it. So you find that while all points along here will satisfy this condition, you find that the point itself doesn't. And for the reason, we want to put a unshaded circle here. Right? So your locus of point would look like this. Okay? You want to put an unshaded circle to signify that this point is excluded. It is not part of your solution. So what you have here is actually a line that goes on forever here, but it actually terminates over there. Such a structure is called a half line. So the locus of points that satisfy this equation, right, is actually a half line. Why half line? A full line goes through all the way. This is just half of it. Okay? In this case, this is a half line starting from where? Starting from 3 minus I. Okay? It is a half line starting from 3 minus I, and what else can you say? And it makes an angle of pi over 3 with the positive real axis. So to describe this locus, right? To describe this locus is a bit more effort, no? It is a half line starting from this point, and it makes an angle of so much with the positive real axis. So in general, how do you write down such an equation in general? In general, the equation of a half line will look like this. It will look like this. It look like argument z minus z naught equals to theta. So such an equation represents a half line. Half line starting from z naught and making an angle of theta with the positive real axis. Right? This is the translated positive real axis. This is a half line. It makes an angle of pi over 3 with the translated positive real axis. So this is how you can describe this locus. And that is your example 3.1. In example 3 part 2, you are given an equation of this form. You compare these two equations, right? You find that they look quite alike. You just need to do that simple tidying up. You can rewrite this thing as argument of z minus 2 plus I equals to minus pi over 4. So by comparison, you will realize that this represents a half line starting from minus 2 plus I. So you draw your Argand diagram. This is the imaginary axis. This is our real axis. So minus 2 is roughly here, plus I, say here. So this is the point, minus 2 plus I. So from here, you want to draw a half line and making an angle of minus pi over 4. So this half line will look something like this. Where this angle, you have to show that this angle is minus pi over 4. Right? And then you can mark this as your Z. And for this particular question, it is actually not too hard for you to deduce that this has to be minus 1 and this also has to be minus 1. And it's good to always put this as your origin O. So if I ask to describe this locus, you will say that this is actually a half line starting from minus 2 plus I and making an angle of minus pi over 4 with the positive real axis. And that is your example 3 part 2. In example 3 part 3, you are presented with an equation. If you compare this and this, right, you find that this equation and this equation, they don't look quite alike. So when that happens, you must always perform some tidying up. So how do you tidy up this one? I'm going to rewrite this thing as argument of minus 2 Z plus 1 minus I over 2. What have I done here? I have simply performed some factorization. Right. So then on the next line, I intend to write like this. I will write this. You might or might not know this. Hopefully you do. If you have learned your complex number well, you will know that the argument of a product of two complex number, the argument of this times this, right, is the sum of the two arguments. This is actually something you would probably have already known again in lower years, that the argument of a product is the sum of the two arguments. So even if you do not know, doesn't matter. Now you learn, okay, that this is something about the complex number argument. You want to realize that if you have to find the argument of something times another, it's just simply the sum of the two arguments. And then the argument of minus 2. What's the argument of minus 2? The argument of minus 2 is actually minus pi. Sorry, the argument minus 2 is not minus pi, it's pi. I prefer to put pi rather than minus pi, okay? Because we remember, we want the argument to be between minus pi to pi but without minus pi. So argument of minus 2 is actually pi. If you draw the complex number minus 2, right, the minus 2 is here. So this is like an argument which is pi. Okay? So argument of minus 2 is pi plus the argument of whatever you have here is equals to pi over 2. And then now we want to rewrite. Finally, we want to rewrite this thing as, don't blink your eyes, this is going to be argument of, don't blink your eyes, what have I done here? I have rewritten it so that this is a minus. Why I want a minus? Because I want to match with this. Right? So what you have here is the argument of z minus something. Let me write this thing a bit bigger, so in case you can't see. This is I minus 1 over 2. Right? So by writing in this manner, I have written this in this manner so that it becomes comparable to this general form. That this represents a half line starting from Z0. This is your Z0. And making an angle of minus pi over 2 theta, right? Minus pi over 2 with the positive real axis. So now can you imagine how this locus will look like on the diagram? Let me draw for you here. So again, when drawing the locus of a complex number equation, you want to start off by drawing the axis. You have the real axis. You also have the imaginary axis. And then you want to draw this complex number, which is minus half, maybe somewhere here. And half I is somewhere here. This is 0. So again, this point is omitted. And then you want to make an angle of minus pi over 2. Where's the angle minus pi over 2? The angle minus pi over 2 is actually here. This angle is minus pi over 2. So therefore, your locus will look like this. Unshaded circle, and then go down all the way. This is the argument. This angle minus pi over 2. Right? So this is my locus of the point Z that satisfies this equation. And this is example 3 part 3. In example 4, you are given an equation that doesn't look like the earlier 3 that you have seen before. If you recall, in the earlier 3, the first one was the equation of a circle. And in the case of equation of circle, if you recall, right, the general equation looked like this. For the case of equation of circle, it looked like this. For the second one that you saw was the perpendicular bisector, and the equation of the perpendicular bisector looks like this. And for the third one that we did earlier, it was the case of a half line. So if you look at the case of example 4, you will realize that in the case of example 4, it doesn't look like any of the first 3. And when that happens, when you cannot identify the type of locus and the equation represents, you can do something like this. Right? This is actually a complex number equation. From a complex number equation, you can actually think of converting this equation, convert it into a Cartesian equation. So if you see an equation that is a bit unfamiliar, in that it doesn't look at anything of the standard type that you know of, you can do what is called conversion into the Cartesian equation. Alright, how do you convert a complex number equation into a Cartesian equation? The way to do it is by first letting the z or the z to be equal to x plus iy. By letting z to be equal to x plus iy, we will actually learn how we can convert an equation that doesn't look like any of the standard types that you have seen, so that you can actually tell the shape of the locus. So in this case, I intend to convert this equation, which is a complex number equation, into a Cartesian equation. And the way to do it is to replace the z as x plus iy. So I'm going to do it for here. On the left hand side, I'll replace the z as x plus iy. On the other side, I'm going to do likewise. I'm going to replace the z as x plus iy. And I straight away tidy it up into this form. Right. So I am in the process converting a complex number equation into the Cartesian equation. So on the left hand side, to find the modulus of or magnitude modulus of complex number is equals to the square of the real plus the square of the imaginary. Likewise, on this other side is also the square of the real plus the square of the imaginary. And now we can actually square both sides. Upon squaring both sides, I'm going to get x squared plus y squared equals to 4. If you expand it again, if you expand this, and we get minus 24y plus 36. Sorry, 36. It's 36. Right, you just expand both sides, right? Upon expanding both sides, you get this, and then you're going to do some tidying up, further tidying up. Get x squared plus 12 equals to 0. Right? If you were to just tidy up this arithmetic a bit, you get to this line, and this can lead us to the equation of, if you tidy up this further, and this becomes an equation of a circle. This is a circle. The center is at 0, 4. Circle whose center is at 0, 4, and then the radius is equals to 2. So in this example, what I've shown you here is we are able to convert a complex number equation by letting z be x plus iy. I have converted this equation through this calculation into the equation of a circle. So once you are converted into the Cartesian equivalent, and now you understand what shape it takes, you can now draw the locus of z in the Argand diagram. So what you can do is, you can now draw a circle centered at 0, 4. This is my real axis again, real and imaginary axis, right? The center is at 0, 4 and the radius is 2. So 0, 4 is here. So it's going to be a circle that looks something like this. This is going to be 2 and this is going to be 6. You have to demonstrate a bit that this radius is actually 2, right? So here we are, by first converting a complex number equation into the Cartesian equivalent, I am now able to deduce that this represents the equation of a circle whose center is at 0, 4, or rather 0 plus 4i, and the radius is 2. And this is example 4. Let me show you more examples how I can convert, or how we can convert from a complex number equation into the Cartesian equivalent. I am taking the examples from example 1 part 1 and the example 2 part 1. Right, I'm using this example we did earlier on. If you recall, right, in fact you already know by now that this equation represents a circle center at 2i and the radius is 3. And this represents some kind of a perpendicular bisector, and therefore it's a line. I intend to use this example to show you more, to show you more examples how we can convert into Cartesian equation. Like the earlier one, to convert into Cartesian equation, I will first and foremost put the z or z as x plus iy. And then to find the modulus of a complex number, it is simply the square of the real part plus the imaginary part. And then you just need to square both sides. You find that immediately you get the equation of the circle that we talked about in the example 1 part 1. Likewise, in this example, you already know that it is a perpendicular bisector. I'm going to show you the calculation to convert this into the equation of the perpendicular bisector. How do we do it? Same thing. I'm going to let z to be x plus iy. Okay, let me write more carefully. Okay, just write them more carefully. This can be x minus 1 is equals to right. So I have just replaced the z as x plus iy, and to find the modulus of a complex number, the same thing. Square root of this plus square of this, square of this plus square of this. But I'm going to square both sides right away. So I'm going to write this as x minus 1 square equals to x squared plus y plus 4 squared. Then from here, what you must do is you have to actually now expand all of them and then do some tidying up. If you were to tidy up, you should get this. Okay, maybe I should try this. 2x 8 minus 4. 4y equals to 16 minus 4, 12. Right, let me check my calculation. Minus 2x, so it becomes 2x. 8y minus 4y, 4y, then 16 minus 4. Okay, so the equation will eventually becomes y equals to minus half x minus 3. So this is the equation of a straight line, and this straight line actually matches the perpendicular bisector that you've drawn for example 2 part 1. So the conversion into Cartesian equation for example 1 part 1 and example 2 part 1 is quite easy. I'm going to do one more example taken from example 3 to show you how I can convert the third type into the Cartesian equation. So I'm taking it from example 3 part 1. You have the argument of z minus plus I equals to pi over 3. By now, you already know that this is a half line, right? Remember? This is a half line starting from 3 minus I, and it makes an angle of pi over 3 with the positive real axis. So to convert into Cartesian equation, I am going to do the same thing. I am going to replace the z as x plus iy. Right, so I have simply rewritten the z as x plus iy. And from here, right, if the argument of a complex number is equals to this angle, then you want to know that if I take the imaginary part divided by the real part, will be equals to the tangent of the argument. So once again, for any complex number, if you take the imaginary part divided by the real part, right, it will always be tangent of the argument. And this gives me y is equals to root 3x minus okay, I made mistake. Okay, once again, this gives me root 3x minus 3 root 3 minus 1. So this is the equation of the half line that we saw earlier on. However, if you look at this equation, this is actually equation of a full line. So to make it a half line, for this particular question, you have to impose a condition. You have to impose a condition that x in this case, right? X in this case must be more than 3. Why is that so? Let me help you quickly recall that if you do remember to draw the locus for argument of z minus 3 plus I. How does the diagram look like? Let's draw this diagram. Okay, if you could recall, right? If you could recall, to draw this locus earlier on, what we did was we have rewritten this as argument of z minus 3 minus I. And this is the half line starting from 3, 3, and then minus I. It was like this, remember? This angle is pi over 3. Please put this as real and this imaginary. So do you recall, in this diagram that you drew earlier on, this half line starts from this point, and that is at this point, right? The real part is strictly more than 3. This point, remember, is exclusive. That's how actually I got this condition that x must be more than 3. So that this together with this condition gives you a half line. Right? We will not do example 5. We will actually skip example 5 totally, and we intend to move on to the next example, which is example 6. In example 6, again, you are presented with equations. In part 1, you are presented with this, and in part 2, you are presented with this, and these two equations do not look like those standard ones that we learned before. Those standard ones we learned before include the circle, perpendicular bisector, and the half line. So these two equations do not look like any of them. So when that happens, like example 4, we can actually try to convert them into the Cartesian equations. How do we convert? Again, we put the z as x plus iy. For the z conjugate will be, then from here you get x is equals to 1, right? So therefore, to draw this locus, it will be just like this. This is the real axis, imaginary axis, origin. This is your the line x equals 1. So in this case, the locus of points that satisfy this equation is your z. This is example 6.1. Likewise, in the case of example 6.2, they're going to do the same thing. Replace the z as x plus iy. Replace this as x minus iy. You will get in the end y is equals to 1.5. So for this case, the locus of points that satisfy this equation will be the case where you have the horizontal line. This is 1.5. This is real. This is imaginary. So you want to mark this thing as your z. Those z values or the z values that satisfy this equation are all the points that lie along this line. And this is example 6. In example 7, example 7 is actually a proof question. In example 7, you are given that there are two complex numbers, both of them are non-zero, and they satisfy this equation, right? Z plus W equals to modulus Z minus W. And you are asked to prove that Z over W square, you want to prove that Z over W square, you want to prove that this is a negative, to prove that this is a negative real number. Okay, right, how do we go about it? Okay, because both of them are non-zero, I could start off by dividing throughout by W. right? If I divide throughout by W, what you see now is actually the complex number Z over W, the complex number Z over W. If now I ask you to draw the locus of, if I ask you to draw the locus of the complex number Z over W, let's draw a diagram for the locus of the complex number Z over W that satisfy this equation. What do you think it look like? If you see Z over W as a complex number, you will realize that the locus of Z over W, if you look at this one carefully, you see that this one is very much the case of A. Let me rewrite a bit more. If you rewrite the equation in this form, you will see that this is actually the equation of a perpendicular bisector. The perpendicular bisector between 2 points. Which are the 2 points? The points are -1 and 1. So let's draw the locus of points Z over W that satisfy this equation. And as I just said, this is actually the perpendicular bisector of -1 and 1. Tell me, where do you think is the perpendicular bisector of the 2 points -1 and 1? Obviously, it is going to be here on the vertical axis. So the locus of the complex number Z over W that satisfy this equation lies along here, right? And you realize that because it lies on the vertical imaginary axis, then this implies that Z over W must be equals to a multiple of I. And now, upon squaring this complex number, Z over W, upon squaring this complex number, you get minus K squared. And this, you see, is actually a negative real number. Right. And this is how it complete the proof for example 7. In example 8, there are altogether 4 parts. And you will realize that in the case of example 8, all of them involve complex number inequalities. Alright, so unlike the earlier examples, in the case of example 8, we are dealing with inequalities. Okay, not to worry if you have already get a hang of the first few examples. Doing examples that involve inequalities is not hard at all. Why is that so though? Because by now you already know the geometrical meaning of this. I'm going to rewrite this as like that. So let's understand the geometrical meaning of this statement or this inequality. In the middle, right? Written in this manner, z minus something, right? With a modulus. This middle expression represents the distance from this complex number to z. This modulus z minus this complex number, once again, it represents the distance from this to the complex number z. So taken together as an inequality, it means the distance from this minus 3 plus I to z must be more than 1 and lesser than or equals to 3. So you want complex number whose modulus from this point is between 1 and 3, inclusive of 3. Now, if I just see this whole thing as 2 equations, right? If I rewrite this thing as 2 equations, if I just disregard the inequality for a moment, I just write this as 2 equations. the first equation, you will recognize it quickly that this is actually a circle from this with center this point, and the radius is 1. This represents a circle with center this, and the radius is 3. So all put together, you will realize that actually to find the locus of the point Z that satisfy this inequality, let's see what happens, right? It's going to be like this. So it will be something to do with the circle at center minus 3 and 1. This is the center, real, imaginary. So for the first one, right? It has to do with a circle, center at minus 3 plus I, and the radius is 1. How does a circle like this look like? It looks like this. Right. Of course, this radius is 1. Okay. Then the other one is a circle, also center at the same point, but now the radius is 3. So with radius 3, the circle will look like this. Okay. I hope I'm drawing a good circle. Alright, so for the next one, it's also having the same center, and now the radius is 3. Let me show you that this radius is 3 by putting out marking like this. This is radius 3. Now to go back to the original inequality condition, you want the distance to be between 1 and 3. Therefore, all those complex numbers that will be between 1 and 3 units away from this point, all the complex number must lie within here. Right, so you do shading like this. So you find that in the case of inequality, the only difference is you actually have to do, in this case, shading. So the locus of the point Z that satisfy this inequality will be all the points inside the red shaded region. Every point inside the shaded region, you'll find that the distance from any of these points here to the center, right? It'll be more than 1, it'll be actually lesser than or equals to 3. I want to highlight to you this thing. No? You want to realize that when this is a strict inequality, I've drawn this as a dotted line inside. You see, the inner circle is dotted line. And then when this is lesser than or equals to, you'll find that outer circle is a solid circle. So in drawing this locus, you want to take note of these few points. Right, dotted solid line because of this, and you have to do the shading. And this is example 8 part 1. In the case of example 8 part 2, you are given an inequality, but in this case, you find that it is very hard to make interpretation based on just like this. So when you see an inequality or B equation that's hard to make any interpretation, you have to do some tidying up. In this case, the tidying up involved will be like this. On the left hand side, I intend to take out 3i. So that I'll be left with z minus 2i. On the right hand side, I will take out minus 3. So that I have z minus I over 3. Okay, how do you judge if you are right in the arithmetic? You take this to times with z, you get the first term, right? You take this, you times with this one, you get back 6. Likewise, you take this times this is your minus 3z. You take this times this, you get your plus I. So I am correct. So now at this stage here, what you can do is you want to actually do a cancellation. This and this are equal. Why is that so? It's because the modulus of this 3i, the modulus of 3i is simply 3. And of course, the modulus of minus 3 is also 3. So what are we left with? We are left with this inequality that modulus of z minus 2i is lesser than modulus of. Okay, let's try to understand, let's try to make sense of the geometrical meaning. On the left hand side, it says distance from 2i to z. Remember, an expression like this, right, means the distance from this to the other complex number. On the right hand side, it is the distance from this to this. So put together, what the statement says is the distance from 2i to z is lesser than the distance from I over 3 to z. Right? And to draw this locus, right, you want to start off by putting this like a equality first. If this is equal, then you recall that this one looks like the standard, one of the standard loci you've seen earlier. This represents the perpendicular bisector between the 2 points, namely 2i and I over 3. So let's draw this. Okay. Let's mark the point 2i. This is 2. This real axis and this imaginary axis. And let's mark the other point 1/3. Okay, if this is equality, right, you have a perpendicular bisector between these 2 points. Where is that perpendicular bisector between these 2 points? If a line that is going to be like this. And this value will be 7, this point, right? This point is 7 over 6. I hope you can see this is 7 over 6. And then you recall what it says here is the distance from 2i to z is smaller, right? So which means your z is nearer to which complex number? Your z will be nearer to the complex number 2i. So therefore, you want to shade the region which are nearer to 2i. This demarcates this on this line, right? There are points which are same distance from these two. But now you want points which are nearer to 2i. Right? You want points which are nearer to 2i. So therefore, points nearer to 2i must be those points that are here. Right? Those points in this shaded region, right? They are nearer to 2i. And once again, you want to note, because this is a straight inequality, the demarcation is marked as dotted, meaning to say that points along here are not admitted into this inequality, because for points along here, it's not straight inequality, it is actually equality. So, therefore, this locus, right, the locus of z that satisfies this inequality is the red portion without the dotted line. So bear in mind, dotted line is important for this because this is a straight inequality. And this is example 8.2. In example 8.3, you are given an inequality that involves argument. And if you could recall, in the earlier example, right, those loci that involve argument are likely to do with half lines. So for the given inequality in example 8.3, firstly, I have rewritten this plus 1 as minus 1. So now to speed up the process, just imagine if you cover this, right, and you put this, imagine this as an equality, then you see that this is actually a half line starting from minus 1. and the angle it made is minus pi over 6. And then if you were to cover this portion and imagine this to be equal sign, it will become a half line starting from minus 1, and the angle involved is pi over 3. So taken together, what you want to draw is actually two half lines. This is real and this imaginary, starting from the point minus 1. So minus 1 is here. You want to draw a half line starting from this point and has an angle of minus pi over 6. Minus pi over 6 is something like this. This is minus pi over 6. And then starting from the same point, you want to draw a line with an angle of pi over 3. So pi over 3 will look something like this. Pi over 3 will look something like this. This angle is pi over 3. You want to realize that once again, when this is a straight inequality, right, it is dotted. Right, dotted. Dotted line to represent straight inequality. Then what you want is, you want those points, you want those points that are in between these two half lines. So where are those points? How do you indicate those points within these two half lines? You will shade all these. You want to be very careful that this point is actually exclusive, right? Let me draw it more carefully. This point itself is actually exclusive. Right. Okay. So for example 8.3, it is simply a half line. Let's look at example 8.4. In example, 8 part 4, okay? 8 part 4, you are given an inequality that's like this, minus 2 real z plus 2 minus I. So in this case, right, if you see an inequality that's like this, and this thing doesn't seem to resemble any of those standard ones, what you can do is you can actually try to express this into the Cartesian equivalent by letting z to be x plus iy. So let me write this thing as real of x plus iy. Okay, so I've just re-expressed it by putting z as x plus iy, and this says the real part of this whole chunk. The real part of this whole chunk is just x plus 2. So now it reduces to this inequality, and this is further reduced into just like that. So what does it mean? You want those regions where the real part, x represents the real part of a complex number z, where the real part is between minus 4 and 1. So how do you draw it? This again is real, this imaginary. So 1 is here, minus 4 is here. This is straight inequality. This is minus 4, this is 1. Straight inequality, I put dotted line. This is non-straight inequality. I'm going to put in a solid line. And this says is between minus 4 and 1. Okay, let me redraw this. This line doesn't look good. Let me redraw this line. Okay, so you want to actually have the region where the x value ranges from minus 4 to 1, but without minus 4 and with 1. Without minus 4 dotted, with 1 is solid line. So you shade this region. So this represents those z that will satisfy this inequality. And that completes example 8. In the case of example 9, you are first and foremost given this equation, right? By now you are already familiar. Such an equation represents a circle. If you were to rewrite this a little bit, right, you will realize that the center of the circle is 3 minus 3i. Be very careful, no, is 3 minus 3i. Because if you were to write this as z minus open bracket, right, 3 minus 3i close bracket. And this is how you have the center of the circle here, 3 minus 3i. And this tells you the radius. So this is a circle centered at 3 minus 3i, and the radius is 2. So let me indicate the radius is 2 by doing this and say that radius is 2. Okay? Now, then this question is not just simply drawing the locus. In this question, you are interested to find out something about this quantity. To find out about this quantity, you want to realize that, right? You want to realize that this quantity, if I were to rewrite this, it will become okay. If I were to rewrite this, if you were to rewrite this manner, you will realize that this quantity has a geometrical meaning. What is the geometrical meaning? The modulus of this represents the distance from -1 to z. In question number 9, where are your z or the z values? The z values are those z values that satisfy this equation, and therefore the z values are all the values on the circumference of this circle. So all your z values are on the circumference of the circle. So given that z are values on the circumference of the circle, you are trying to find the greatest and the least distance from -1 to z. The greatest and the least distance from -1 to this circle. From a point -1 to the z values here, how can you obtain so-called the maximum distance from -1 to some z on this circle? And you want to know that given a circle and a point, the maximum distance is achieved by joining up this point through the center and to the other side of the circle. This red line tells you or gives you the maximum distance from -1 to z, which are points on the circumference. So therefore, to find the maximum distance, the maximum value or the maximum distance, oops, I wrote wrongly. So the maximum distance is given by the distance from -1 to the center of the circle, then plus 2, right? So this would be the distance of 5 plus 2. Why is it 5 plus 2? No, you want to know that from this point to the center, right? It is the case of 4 by 3. 4 by 3 gives you a distance of 5. This is 5, then plus another radius which is 2, so it's 5 plus 2, which is 7. And then you are also asked to find the minimum distance from -1 to z. Given the point and the circle, you want to know that the minimum distance is actually attained here. this blue line from the point in question to this point on the circumference, right? From here to here, this is the shortest possible distance between this point and this circle. So judging from the diagram, it therefore becomes the distance from here to the center, then you subtract away a radius. So the minimum distance is actually 5 minus 2. So there you are, the maximum and the minimum value of z plus 1 modulus and z plus 1 modulus. Okay, that is example 9. In the case of example 10, you are given this equation, and you know by now that such an equation represents a circle centered at 3, 4i, and the radius is 2. So I have drawn for you the circle centered at 3 plus 4i and the radius is 2. But that's not the end of the question. In this question, in part 1 of this question, right, it asks you for the greatest mod z. You want to realize that in this question, the complex number z, they are actually points on the circumference of this circle. So all points on the circumference of the circle satisfy this equation. And among all these possible z, you want to find the one that will give you the greatest modulus of z. In fact, you want the greatest value of mod z itself. So to answer this question, part 1, right? First and foremost, you must understand what this expression means. Modulus of z, right? Modulus of z, if you were to rewrite it, modulus of z, if you were to rewrite it, it becomes modulus of z minus 0. So modulus of z is the same as modulus of z minus 0, and this expression means the distance from origin to the complex number z. So therefore, part 1 requires you to find the greatest distance from origin to the complex number z. So from origin, right? From origin, you want to find the greatest distance from origin to some z in this circle. Like the earlier question, the greatest distance is always achieved from the point in question through the center to the other side of the circle. Once again, the greatest distance is achieved from the point in question through the center of the circle to the other side. From here, through the center to the other side. So look at this triangle here. The distance from the origin to the center is already 3 by 4 gives you a distance of 5. Then plus another 2 units. Can you see? 5 plus another 2 units. So therefore, part 1, right? Part 1, the greatest modulus of z, based on our analysis is actually a distance of 5 plus 2. So it's actually 7. It's very similar to the earlier question. Alright, next we want to look at part 2 of example 10. In part 2, you're asked to find something to do with the argument. In this case, it's argument of z plus 1. So I want to actually now rewrite this complex number, z plus 1. Alright, I want to rewrite this complex number as z minus 1. Okay, rewriting in this manner allows me to understand what it means by this. This means a complex number drawn from minus 1 joining z. So from the point minus 1, where's the point minus 1 from here? This point is minus 1. From point minus 1 to z. So from point minus 1, you want to join up to some z value on the circumference. And among all the possible lines that can join from minus 1 to z, there are many possibilities, right? Many possibilities. You want to actually look for the one that will achieve the greatest this and the least this. Starting from minus 1, how can I draw a line such that I achieve the greatest argument of this complex number? starting from -1, right? To achieve the greatest argument of this complex number, starting from -1, I can do so by drawing a tangent line from the circle to -1. This angle here, right, actually gives you the maximum possible argument of this line here, right, and the angle that it makes. This one is the greatest argument you can make for -1 to z. Right, this is one extreme. So that gives you the max. Now you want to actually also know how can you get the minimum. How can you achieve the least or the minimum of argument of z minus -1. So again, from -1, right, you have to draw to some point z on this circle so that this argument will be the least. And such a line will be like this. Okay, right. Let me polish out a little bit more. This gives you right. Okay. Right. And then this is your. Okay. So your least argument is actually achieved here. This is the least argument you can achieve. Can you see? So on the one hand, this from -1 to a point here, right, achieve the greatest argument of z minus -1. From the point -1 to here, right, it achieved so-called the minimum argument of this. And the question wants you to find the difference between these two arguments. So the question is asking you for which angle? The difference between these two angles, right? The difference between this angle is actually therefore this angle. So the question is actually basically asking you to find the green angle. The green angle represents the difference between the greatest and the least argument of z minus -1. So how do you find the green angle? To find the green angle, you want to actually make use of this strategy. From the center of the circle, I'm going to draw a line to here. Okay, to here. Right. Let me polish up this one a little bit. It's a bit cluttered and a bit untidy here. Right, so there's a point -1. Right, okay, so now our intention, our strategy taken is to first and foremost join from the center to the point -1, and then realize that if I were to draw this over here to where it meets a circle, this one is actually a 90 degrees. Okay, let me erase all this one because it may cause distraction. So what I've done here is I've actually drawn a right angle triangle where this is actually the radius and this is therefore unique, distance 2 unique, and then we also know this distance, right? We also know this distance. How do you find this distance? This is 4 by 4, so this distance is actually 4√2. Right. So let's recall again. The intention is to find the green angle. To find the green angle, what I can do is you can first and foremost find this angle first. Let's call this angle, give this angle a name. Let's call this angle theta. Let me put back the missing thing. this length, remember just now I calculated, no, this length is actually 4 root 2. Let me write here again. 4 square root 2. So 4 square root 2 is actually from here to here. So the strategy here is looking at this right angle triangle. Can you see a right angle triangle, right? And call this angle theta. The green angle that you want to find is actually 2 theta, right? So the difference between the largest and the least is actually 2 theta. Can you see? Because this angle is theta, I could produce the same triangle and I can get another angle theta here. Can you see? Another angle theta here. So to find the difference between the largest and the smallest of this fella, which is the green angle, I can do it as 2 times theta. Theta is here, there's actually another theta here, right? So maybe for completeness sake, let me maybe produce it here, show it to you here again. And this is another angle theta, right? This is another angle theta. Right. So to find the green angle is just 2 times of theta. And how do you find theta? If you look carefully, right? If you look carefully, because this distance is 2, and this distance, which is the hypotenuse, this distance is actually 4 root 2, right? So you find that theta is actually sine inverse of 2 over 4 square root 2. Right. So therefore you can use a calculator to press this number for the angle. Okay, so if you use a calculator, this becomes I get an answer of 41.4096 degrees. Okay, I simply use the calculator. Okay, so this is the difference between the largest and the smallest argument of z minus minus 1. And that completes example 10. In example 11, they are given that there is a complex number w that must satisfy this condition and this condition. For the first condition is easy. It represents, if you recall, right, a circle. In fact, by now you're already familiar. This is actually a circle centered at 2, and the radius is also 2. Can you see? Radius is 2. So I've drawn for you the locus of point W that satisfy this equation. And now you also have a second condition that W must satisfy. In this case, if you look carefully, right, this is the usual equation of a half line. Maybe you want to rewrite this as argument of W minus 0. By writing in this manner, you therefore can see very clearly that this is a half line starting from the origin 0. Starting from here, we want to draw a half line starting from here, and the angle made with the positive axis is pi over 3. So that half line will look something like this, where this angle is pi over 3. So in this question, because W must satisfy both conditions, it therefore would mean that the point W must be here. The point W must be here. This is the point W. So the question right now is, this question wants you to write down the modulus of W first, then followed by the complex number W itself. So how do we find the modulus of the complex number W? To do this, you want to realize that in this diagram, if you were to join this up, my diagram may not be very accurate, not drawn to scale, but you can still see what's going on here. If you join this thing up, you want to realize that because this is the radius, this is 2. Because this is the radius, this is also 2. So therefore, in this triangle here, immediately you know that this length and this length are both 2. And therefore this triangle is an isosceles triangle. This is 2 and this is 2. So let me put it down the markings. This length is 2 units and this length is also 2 units. So therefore it's an isosceles triangle. And because it is an isosceles triangle, if this angle is pi over 3, this angle must be also pi over 3. If these two angles are pi over 3, then it means the third angle, right? If this is pi over 3 and this is also pi over 3, that means this third angle must also be pi over 3. And therefore, you want to realize that in this case, this triangle that you see here is actually an equilateral triangle. So you need to see an equilateral triangle firstly. Right? You can see in the diagram there is an equilateral triangle in the diagram. Because this triangle is an equilateral triangle where all the 3 sides, you want to realize that the 3 sides therefore must be equal, then it becomes necessary that this distance and this distance and this distance, right, they are all the same. Therefore, this distance is actually 2. And because this distance is actually 2, this distance is actually the distance from origin to the complex number W. This distance is exactly the modulus of W, which is the same as this, which is also the distance from origin to W. From origin to W, the distance is also therefore 2. So I have found the modulus of W quite quickly. Now that you have the modulus of W, the question wants you to find the complex number W itself. So to do this, I want you to see this triangle. This one, right? From the complex number W, I'm going to drop a perpendicular down and then close up. Okay? So again, I intend to draw a triangle from here to here. Then from here, I draw a perpendicular down and then close up. So this triangle will look like this. This is pi over 3, right? This is complex number W. This, we've proven that this is 2. So to find the complex number W, what we need is actually to find the horizontal distance here. This horizontal distance is the same as the distance from here to somewhere there where W dropped down. And because this is isosceles triangle, when you drop a perpendicular down from the vertex of triangle to the other side, you drop perpendicular down from here to there, right? You'll find that this length has to be equals to 1. This length is actually 1. Right. Let me write it down. Even if you do not know or cannot see from there, right? Based on this triangle, right? Based on this triangle, this length here is the same as actually 2 cosine pi over 3. Right? You can see this other way, no? If this is 2, this length here is 2 cosine pi over 3. and 2 cosine pi over 3 is also 1. Then using simple calculation, your theorem, right? You know that therefore this length has to be root 3. So all in together, therefore the complex number W, right? The complex number W horizontally is actually 1 unit and vertically is actually root 3 unit. So the complex number is actually 1 plus root 3i. So what I've done here is I have actually made use of this triangle here, which is reproduced here, right? To find my horizontal and vertical distance, and therefore I can tell that the complex number W is exactly just 1 plus root 3i. And that completes example 11. Okay, in the case of example 12, just like example 11, you are given two conditions or two equations that the complex number z must satisfy. Let's look at this one first. This is actually a circle centered at -2 and the radius is 3. Centered at -2 and the radius is 3 units. So maybe I will want to actually put this thing down as 1 to tell that the radius is actually 3. Right? So in the first in this condition, right, you have actually a circle centered at -2 and the radius is 3. For the other one, this represents a half line starting from 2. Remember? Half line starting from 2 and making an angle of 3 pi over 4. And then this is my half line. So in this question, you have a case of a complex number z that satisfies both conditions. And such complex number z based on the question, right, are these 2 points 1 and 2. And in this question, right, the aim is to find these two complex numbers, this and this. Now, many times, right, we can use a geometrical consideration to solve for information we need. Like in those earlier questions, especially question 11, using geometrical consideration, we were able to find W quite quickly. But sometimes you can also do it this other way by first and foremost converting both of them into their Cartesian equation first, and then solve the Cartesian equation. When would you want to take such a strategy? You will probably want to do it because sometimes even with the diagram, with whatever you know about the question, it is sometimes quite hard in this question to try to do it by geometrical consideration, and you perhaps may want to consider therefore other ways of doing this. And one other way to doing this is to first and foremost convert them into their Cartesian equivalent, right? So let's convert these two equations into the Cartesian equivalent. This first one is this circle is quite simple. It is just x plus 2 square plus y square equals to 3 square. This is actually the equation of the circle. Let's call this equation 2. Then for the equation on top, you can now convert this equation into so-called the Cartesian equivalent. It will be y over x minus 2 equals to tangent of 3 pi over 4. And this equation can be tidied up to become y equals to minus x plus 2. So trying to solve these two conditions for the point z as shown in the diagram, you could do it using the equivalent Cartesian equations. So what I've done here is I've converted both equations into the Cartesian equivalent. That on one hand, right, this is actually a circle, right? The circle, and this case is actually a half line. So let me just be sure that I converted it correctly. Okay, so I believe I've done so correctly. So now I intend to solve these two equations simultaneously for my x and y. So how do I do it? I can just replace this into here. I will get x plus 2 square plus minus x plus 2 square equals to 3 square. Right, let me write like 2 carefully. This 2. So you can do your expansion, and then you'll get 2x square. 2x square is equals to 1. Right, you just expand yourself, no? You just expand normally. Therefore, you will have the value for x now. X is equals to plus minus 1 over square root 2. Now that you know your x, you can now find your y. If x is 1 over square root 2, if x is 1 over square root 2, right? I plug it back here into here, right? I will get minus 1 over square root 2 plus 2. And then likewise, if x is minus 1 over square root 2, this becomes 1 over square root 2 plus 2. So therefore, the two points here, right? The 2 points here, this point could be the complex number 1 over root 2 plus I of this. Because you are solving for the complex number z, you should at the end of it write this as complex numbers. You should really write the 2 points as 1 over square root 2 plus minus 1 over square root 2 plus 2i. So this one is for this complex number. Yeah. And then for the other one, likewise, you can do the same thing. You can put this down as minus 1 over square root 2 plus 1 over square root 2 plus 2i. So what you realize is sometimes given equations that are not so nice to solve using geometrical consideration, you can actually do it likewise from the Cartesian equation. And this becomes the 2 points here and here. This point is this, and this point is actually this. Right? So I've shown you this another way to solve for the intersecting point between two loci. You can actually use their Cartesian equivalent, and that completes example 12.